As he said, my name is Bert Pablo. I am the staff astronomer at the AAVSO, and we'll get into what exactly that means pretty much right now. So, what is the AAVSO? Well, on the website, if you go to it, there's a motto. The motto says, the mission of the AAVSO is to enable anyone, anywhere to participate in scientific discovery through variable star astronomy. Now, this is a lot of very specific language that tries to be as open and inclusive as possible without actually telling you really much of anything at all. So I like to think of the AAVSO as a community that learns together. We have around 1,200 members, 800 observers, people who look at the star and provide data to us, 200 volunteers, and 10 different staff members. Now, this is just sort of the group as a whole, but we have a lot of different ways in which they interact. We have forums, which are used quite often. We have Slack channels. We have different various ways that people can contact each other or be in touch with each other through different tools on the website. And we also have an annual meeting, which takes place every year, where people get together and they talk about science and what they're working on, what their research projects are, more about their telescopes and what they're doing. This was an auto-include by our marketing director, which is that our next annual meeting will be in Huntsville, Alabama at the Space and Rocket Center. So if you've never been there and you're interested, please feel free to give it a try. So, what does the AAVSO do? Well, the AAVSO is in the data game. What we essentially do is that we allow people who have their own telescopes and their own equipment to submit data to us, and we then make that data available immediately and freely to anybody and everyone who wants to use it for any sort of scientific purpose or educational purpose. And we also partner with a lot of different researchers who want to do very specific projects and they don't have the resources to do them themselves, or they need something very specific from the community. Now, we have several different ways that you can do this. We have solar observations, we have exoplanet observations, which there will be a talk on a little bit later. We have spectroscopic observations, and if you look in the center here, this is probably one of the most famous variable stars, at least for the organization. This is SSIG. It's a recurring nova, and as you can see, over time it does big stuff, often. So people love to observe it because it changes a lot over time. So how do we do science? How do we work with people? Well, I think that we can sort of break it into three different categories. As the previous speaker said, we have a lot of archival data. Our data goes back over a century, most of which were taken by amateurs. We even have some data dating back to the 1500s, I believe. That was taken from various and sundry almanacs that people had back in the day. It was before us. We're old, but not quite that old. But we have more than 63.5 million photometric data points there, dating back through history, so you can use that at any point to look at any star that you want. This is data that you can use that's already freely available. Now, what happens more often now is that a researcher will come to us and they'll say, hey, I have this star that we're going to look at with the Hubble Space Telescope, or we have data on this thing from a different project and we need concurrent data such as photometric points or spectroscopy, and we need someone to help us take it. So we'll set up a campaign that's very specific to a star. People will get an alert, an email or something saying, here are the details, here's what you need to do. If you could observe this star for us, we would be very happy about it. And that's how a lot of things work. This works very well for singular objects or when there are just a couple of people asking for things. The third way, and the way that I'm going to speak most about today, is through larger collaborations. The idea here is that when there are big projects involved and people need to observe things for very long periods of time, it is extremely difficult to get telescope time for continuous observations. When you get time on, James Webb or Hubble or something, they measure it in terms of orbits. You'll get a certain number of orbits of the telescope. An orbit of the telescope is typically 90 minutes. So that kind of tells you something about how much data you're getting and how expensive it is to run. You simply just can't look at a star as long as you want for, long periods of time and hope that something will happen. Even if you are sure that something's going to happen, nobody's going to give you time to do that. So let's look at a normal campaign, and we will sort of see the difference between that and the sort of collaborations that I'm talking about. If you are interested in variable stars at all, you might have heard of an object recently called T-Core-Bohr. This object has been in the news consistently for months because Brad Schaefer is great at PR, and it's a pretty cool object. So essentially what's going to happen is that you have this star, and it is going to explode. We know it's going to explode because it's exploded in the past. It was 80 years ago, but we have data for it in our database. And there are precursor signs that say it's going to happen again. So once that happens, you see that there is this sort of thing that's going to happen. It's rare, and it has a lot of interesting data associated with it. So it makes for a great campaign. You can say, hey, we know this is going to happen. We can give you a good window as to when it's going to happen. We only have one object, so it's really easy. And we just want you to observe in as many bands as possible, as much as you possibly can. And this results in a lot of observations and a lot of people waiting for something that will eventually happen, I promise. Actually, I don't promise, but Brad does. So this is how a normal campaign works, right? And it's very easy to do because we only have a singular object that we're looking for, and it's easy to get everybody all involved. But it's this sort of other thing, these sorts of collaborations, where it becomes a little bit more difficult. And sort of the highlights of these is that you want to look at not just one object, but a lot of objects, one of which might do something. It's really, really important if it does, but we don't know which one it's going to be or when it's going to happen. So this, one such project is what's called the Supernova Early Warning System. And the goal of this project is to find the next galactic supernova. Now, in order to understand this whole thing, we have to know what a supernova is. So there are sort of two main types of supernova. You have the kind where you have a singular object like a white dwarf that is accreting matter onto it. It slowly gets up to a point and it explodes. These objects are great for a lot of different reasons. I'm not going to talk too much about them. The second kind of object are your supermassive stars that are effectively dying, and they die in the form of this giant explosion. So essentially what happens with these stars is that they get all of their energy from fusion, right? They'll fuse hydrogen to helium. They'll then fuse those elements to carbon and nitrogen and oxygen. And they'll fuse all the way up to iron. And it stops at iron because when you try to fuse iron into anything else, you actually lose energy in the process. So it's not something that can be done and keep the star stable. Now, when you have a massive object that has been using this pressure due to this fusion to keep it alive and keep it big and massive, and then it no longer does that, it essentially just collapses in on itself. And there's this giant explosion which happens, and that is, in effect, the supernova that you will see. Now, these stars are really cool, and this object is really interesting, but a lot of it we don't know a whole lot about because while it happens a lot, it doesn't happen a lot here. The one thing I want to point out is that when these supernovas happen, it creates this sort of shock wave that goes out, and this shock wave basically sort of prevents the photons from leaving for a long period of time. But then there are these little particles called neutrinos which don't interact with much that can get through. That'll be a little bit more important in a minute. So these supernova are extremely bright. They rival the luminosity of an entire galaxy for a very brief window when they explode. It's a really cool thing that happens. You can see them in other galaxies relatively often. There are, just to give you an idea, while it's a sort of long time scale in the grand scheme of astronomy, we look at so many different galaxies that these things happen relatively frequently. There are 955 of them that have happened just this year. And because the naming scheme is as it is, the latest one, at least unless one has happened even more recently, is 2024 QAT. They basically just go A and then AA and then AAA. So you get the idea. Not the most realistic naming system, but it's the one that works for them. Now, in the grand scheme of things, you might think, okay, so we have a bunch of these objects, right? Why do we care about finding one in the galaxy? Well, the simplest reason is that since all of these things are extragalactic, we don't know what they are. We see the explosion, we don't know what caused the explosion. Effectively, they get so bright that we wouldn't have any hope of seeing the star that caused it, even if we could see the galaxy itself. This is even true in something that was relatively close, like supernova 1987A. We have pictures dating back. We cannot see what the star was. We do not know. So, the goal of this project is twofold. The first is to essentially monitor progenitor objects. We don't know what's going to explode, but we have some reasonable ideas that they're going to be these late-stage supermassive stars. So probably supergiants, specifically red supergiants, because red supergiants are older and they have been in their life cycle longer. So we assume that these are the stars that are going to explode, and there's reasonable reason to assume that. In order to know what these stars are going to do, we want to sort of study them, right? We want to consistently follow them for as long as possible so that when they do explode, we have data dating back to before the explosion. We know what was happening. We can sort of see what was going on with these stars, which is something that right now we just don't have. So it's kind of a missing piece of the evolutionary puzzle. And the second thing is that we want to be able to get on sky as soon as possible when a supernova like this happens. It's a very rare event, a sort of once-in-a-lifetime event, or even longer, and we want to be ready. So as soon as a supernova goes off, We want to be able to be on sky as quickly as possible, taking as much data as possible so that we have as much data about the explosion itself as we possibly can. So, can we get this advance warning? Well, as it turns out, yes. So, snooze, as the name does not necessarily imply, but a lot of the collaboration aren't really astronomers, at least in the typical sense. They're mostly neutrino scientists, and you might think that astronomy is a fairly small field in the grand scheme of things, and it is, but everybody has a specialty, and every specialty is very, very, very specialized. To put things into perspective, I had some friends who studied specifically neutron stars, right? So similar to this sort of topic, but not quite the same, a remnant. And at one point, I got an email from them, and they said, hey, so we tried to look at our neutron star because there was a big X-ray burst from it, and there's a star in the way. We don't know what to do about that. Can you tell us what this star is? And I was like, sure, I can do that. So people hyper-specialize a lot in astronomy, is the point that I am trying to make. And the neutrino scientists are effectively using us to get the data that they don't really know much about themselves. So the point is that because these neutrinos are essentially able to escape the supernova much faster than a photon does, we'll get neutrinos from this object that we can detect before we'll ever see any light from it. Now, we don't get a lot of warning. It's maybe an hour or two, maybe 10 hours at the max, but it is something. It's enough that people can be prepared. So, how do we take advantage of this? How do we use this early warning to actually do something? Basically what we do is we need to figure out how to trigger on these neutrino pulses. And effectively what they decided to do in this sense is to basically create a network. Now, there are multiple neutrino experiments across the globe. All of these neutrino experiments have pluses and minuses to them, but all of them can detect this sort of galactic supernova. It's a very big event. Almost all of them were able to detect the supernova 1987A. As it turns out, no one thought to look ahead of time. That wasn't really in there, but they looked at the data afterwards and they're like, oh yeah, there it is, right there. So it's a sort of thing that if you know what to trigger on, you can see. Now, there are a lot of false positives that can come out of experiments like this. So having multiple different experiments across the globe gives you two very important things. The first is it gives you redundancy, right? You can have an error in equipment or a weird readout in one of these, but if it happens in two or more, you know that it isn't an error. You have some confidence that you can say something about this. Because one of the things that they like to say is that if we try to trigger this and we're wrong, no one's ever going to believe us again. And observatories will be very mad, right? Because it's one of these things that requires a lot of time and effort for them to do. So the system has to be robust, it has to have redundancy, and it has to be fast. They need to be able to identify these things quickly, confirm with other places, and then send out an alert. And the second thing that having multiple experiments does for us is that it allows us to triangulate on the sky. Neutrino experiments have very, very, very poor resolution. They'll give you a 30-degree field of view that could either be in the north or the south, for instance, right? That's as good as they can do, because they don't even know the direction they came from because the Earth is opaque to neutrinos. So it could come from any direction. Having multiple experiments at least lets us triangulate whether it's the sort of northern part or the southern part in this basic analogy. And that's crucial because if we know where to look and we have the objects where it's expected, it gives us a way of finding this stuff and getting on sky as soon as possible. So what are these progenitor objects and what do we know about them? Well, they are presumed to be red supergiants. All that means is it was a very massive star that has slowly started to puff up bigger and bigger and bigger as it has sort of stopped fusing its typical stuff and it's starting to get toward the end of its life. We know that there are only about 600 of these in the galaxy, and 600 might seem like a lot, but with respect to the number of stars out there, it's nothing. So that's a plus. We know that these stars, because they are big, they are also very bright. So more than a third of the targets are brighter than 10th magnitude, which means that virtually anybody can observe them. And there's a fairly good proportion of them throughout the sky. So it's not like they're concentrated in one specific place or another. But that comes with some issues, at least some general issues for their observation. Things that are brighter than 10th magnitude are often thought to be too bright from an astronomical context. Virtually every observatory in the world, if you wanted to take photometric observations, they tend to saturate at around 10th magnitude. All surveys tend to saturate at around 10th magnitude, or even fainter than that. I think Assassin is 10th magnitude. ZTF is like 13th magnitude. So a lot of these sort of surveys that you see all around, they don't look at any of the brighter stars, and that's kind of on purpose because there are more stars that are faint than there are stars that are bright. So you're just going to get a lot more stars to look at if you limit yourself in your brightness. We don't know much about when this is going to happen, right? We know it's something that's inevitable. It will happen at some point, but it requires continuous monitoring of these stars to build up a baseline. And not only do we want a lot of data to sort of have just before the supernova erupts, but these stars in particular are things that take very, very long timescales to actually evolve. Some of these things take thousands of days. They have periods of thousands of days. And finally, it is difficult to be, we want instantaneous follow-up, right? So we want to be on the object as quickly as possible. That's very difficult to do. Especially for professional observatories to be like, oh, sorry, we need you to go here and we need you to do it in the next half an hour. Which is where the AAVSO comes in. We essentially can provide a group of people who are more than happy to look at these stars on a regular basis for a very long time because it's a contribution to science that really only they can make. So first are the alerts, right? So SNOOS has what's called alerts, which they do. And that's essentially telling someone, hey, we have a trigger for a supernova-like event in neutrinos. Here's the location, go and observe it. This is something that you can sign up for and get alerts whenever they happen. They also do something called fire drills, which, because these events are so rare, they essentially say, okay, we're going to practice doing these, so we'll tell you, sometime in the next 2 weeks, we're going to have an event, and we want you to see if you can look at it, if you can find it in time, etc. And these are sorts of things that you can do, you can sign up for right away, and you'll get emails that will essentially just tell you these things. And the second and sort of larger scale part of this project from the AAVSO side is this progenitor monitoring campaign. So SNOOS came to us with a list of 600 objects. We said, that's great, but that's probably too many for us to do continuous coverage on all the time. So why don't we start with around 200? So we took the 200 that were the brightest, the ones that nobody else was going to be able to cover well, and start with those. We want to observe these things often, but not too often. Instead of getting as much data as possible for each star, we just want to get 1 to 2 observations a night. It doesn't even have to be every night. Every few days is fine, because again, these stars change over very long time scales. You're not really going to miss anything if you're not observing continuously throughout the night. And these stars can vary a lot. They can vary by several magnitudes. It just takes them a while to do it. So, where are we at so far? So there are 192 stars in the campaign, and we have observations of 188 of them. For context, we started around October of last year, so we have been going for roughly 9 months at this point. And we've done pretty good at getting observations of most stars. The couple that we don't have are because of some very specific limitations, such as they are extremely bright, or they are extremely bright and in very low declinations, so they're hard to get from the northern hemisphere, things like that. In total, we have 3,400 observations, almost in V, and nearly 10,000 observations total. We have around 120 of these objects, which are getting really good coverage. They're getting observations as often as I would like. Now, that isn't 192, but we're actually getting pretty close. So it's a good place to be. So let's look a little bit into some results. And again, I need to preface that these are very preliminary results. And the reason that I need to preface this is that we have this nice little light curve here. This is the light curve of Betelgeuse. If you guys remember, right around 2019, there was this thing about Betelgeuse getting noticeably fainter. It was something that was all over the news. People were worried that maybe it would go supernova. Well, it recovered and came back up. But in the life scale, or the lifetime of Betelgeuse, up here, the SNOOS campaign has covered that much of it. So you'll see that things happen on much longer timescales with these stars. So what I have to show you is a very small snapshot of this so far. So as it turns out, even though these stars are all fairly bright, a lot of them don't have any really known periods. They have periods that just aren't known, either because they're too, they change too much for us to know, or no one's really taken the time to study them or take observations of them. And so for a few of these, we can actually see a period starting to form. For ASEP, for instance, we can say that the period, we can't say it with any sort of certainty, but we can start to say that the period is on the order of around 250 days or so. Now, we still need a lot more data to confirm it, but that's more data, more than we had before. And we can also see some interesting things like CE tau has shown to go all the way down and then start to come back up to where it was. So that is indicative of a full period. So we're starting for these shorter period systems, shorter period still being several hundred days, we're starting to get light curves and we're starting to get periods that we didn't have before. We can also see a couple that have clearly, the periods have either changed with time or they were just completely wrong to begin with. This guy on the right here has a period of 87 days, and we have seen nothing in the over 100 plus days that we have of data. And this guy on the left over here has a period of roughly 100 days, and we have 100 days of data, and we definitely have not seen anything. It started off low, it went high, and we're nowhere close. So this is another sort of thing that we have gotten. We have found out that some of these stars are just simply not what we thought they were. And then it's just kind of fun to look at some long period light curves. It's interesting to think that over 300 days, this guy has dropped, a magnitude and a half, and it just keeps dropping. It's got such a long period that it's going to be hard to say anything about it for a very long period of time. Imagine that. So we have these stars that have super long periods that we're also keeping track of, and they are doing things, but it's tough to say exactly what. So all of that to say, where are we at and where do we need to be? Well, we need to do pretty much 3 different things. One of the main ones is more data vetting for these objects. When you have lots of people observing these systems, what you end up with is that sometimes people make mistakes or things don't go quite right, and it's great because if you have a lot of people, it's easy to spot where there are issues, and you can talk to people and you can find out where those issues might be. The second is to really dig into the statistics of these systems, figure out more about period anomalies, what's going on with them, and figure out which ones are really interesting for having even more observations than we currently do. And finally, as might be apparent from how long these periods are, we need to keep observing. We're at the very beginning of this project, and we're still a ways from being able to say anything concrete. And maybe even if we have the manpower, we can expand to observe even more of these objects. So that comes to you, to people at Stellafane, who may or may not have a telescope or the ability to observe. Have you ever thought about doing so? Because there are lots of different ways that you can get involved. The first is through visual observations. Now, most observations, or I won't say most, but the majority of observations that go into the database are photometric. They're taken with CCDs or CMOS or some kind of digital detector, but people still observe by eye. And it's not the easiest thing to do, but it is something you can do with very minimal equipment. The plus is that for this object, we really kind of need these observations, because if you get to stars that are above 5th magnitude, it becomes very difficult to actually observe them with any sort of digital device. You're going to saturate almost immediately. It takes a lot of effort and time, and a lot of these stars just simply can't be well covered. But if you have multiple people doing visual observations on these stars at the same time, what you can build up is a light curve for these stars that change that gives us very valuable information. And the more people that we have doing it, the better the information is, because we will take averages of all of these data points to really get a full light curve. The second is, for people who are members of the AAVSO, we have AAVSO.net. Now, AAVSOnet is basically a group of telescopes around the world. You can propose to do something with these stars, or, as in the case with this, it's already observing all of these stars, and you can just request data. You can request data immediately on these stars, and you can get them. And then you can do as much as you want. You can submit the observations to us, and you don't even have to do any observations yourself if that's not your thing. It's a relatively easy way to sign up. You can do it on our website. We have this nice little sheet where you can say, hey, I would like to get observations from AAVSOnet, or hey, I would like to observe this star. And it all turns out pretty good. And finally, if you are interested in doing this, or you want to do something like this, you can find out more about the AAVSO and its community there. And you can find out more about the Snooze project here. And if you do not have Wi-Fi, I can give you easy links that you can write down that are at the bottom there as well. So thank you for listening to my talk. I will take any questions at this time. He was asking about the chances of having a supernova and the supernova being one of the objects in the sample. And it's a bit difficult to give you exact numbers. What I can say is that there should be, statistics say that there should be about one supernova in the galaxy every 100 years. Now, we have not seen one in the galaxy in quite a long time. If a supernova does happen, and it is visible, it's likely going to be one of these objects. One of the things that is much more difficult to predict is that there are some stars that we just simply can't see that are directly in the disk of the galaxy. If one of those goes supernova, we would still probably measure the neutrinos from it, but we would not be able to do this sort of progenitor program because those stars just simply aren't visible. As to the statistics of where we stand as to like which star will go supernova, I just don't think anyone really has a good idea.
While you have at least one person observing 188 of those stars, I assume you'd like to have redundancy because people get clouded out. Like how many, do you have like a ideal number of observers per star that you're looking for?
Ideal number of observers per star is probably greater than 5 and less than 10. And the reason that I say that is because you're right, coverage is important, but it's also important to note if someone has an issue with data. If you don't have anything to compare against, you don't know if that data point is real, if the star is really doing this, or there was just a mistake that happened. And it's totally fine, mistakes happen all the time, and that's why redundancy is so important. However, if you have too many people observing a star, what ends up happening, and what happens a lot for us, is that for these stars, people will observe the ones that they're really interested in or that they were really inspired by, like Alpha Ori. Alpha Ori gets probably 20 or 30 people observing it roughly every day, and that's great, but it probably doesn't need that. It doesn't really do much over that time, so you kind of have to balance those things out. Yes?
I thought that I signed up for getting the snooze alerts several months ago, and I have not heard anything from AAVSO. Should I check and try to register again, or something's happened?
So do you mean like the physical alerts of the a neutrino alert, like a go observe here? So technically, the AAVSO does not run those. That is run by the Snooze collaboration. I will double check with them, but I think there was a fire drill in November, and since then there hasn't really been a whole lot actually happening. They're going to be very conservative with sending out alerts because they really don't want a false positive. But I will definitely double check with them and see where that status is. So please follow up with me. I can get your email afterwards. You can just email me and I will check. But I think it's reasonable to say that there probably hasn't been much that has happened yet. Yes.
Are some of these stars candidates for observation with the new generation of smart telescopes, the little thing?
Yeah, especially the brighter ones. I would say that most of these stars have extremely long variability, but it does vary a lot, right? So a lot of these things vary by several magnitudes, so you don't need to have very, very precise measurements to figure out what's going on. And in some cases, it's actually better to have the smaller telescopes because you can observe the brighter stars without saturating as easily. Oh, yes. You in the red shirt. So effectively what happens in a nova is that when you get mass accreted onto an object, at a certain point, it will, once you have enough matter built up, it will tend to explode because you're only collecting on the outside of the envelope. It's not going into the star, and the star can't really support it. So it can only accept so much buildup before it actually explodes. If you want a more detailed explanation of that, I do not have it because the explosion physics is beyond my pay grade. But that's the effective idea. Now, what's really interesting is that some of these things will accrete forever and then will eventually explode because they accreted too much matter and they collapse, and then they'll explode out. But that doesn't happen with recurrent nova. Recurrent nova will just keep having mass go onto it and then explode. And I don't think anyone really knows for sure what the difference is, why some of these stars will explode periodically and some of them won't ever explode and then get too much mass and then just go boom. Yes?
Are the observations you're looking for visual, photometric, or either?
I will take either. Visual observations are especially good for the super bright stars because, as I said, it's very difficult to get photometric observations on them without saturating, even for relatively small telescopes. In this campaign, it really is open to whatever we can get.
So typically, with comparing the star, if you're doing photometry, you're doing differential photometry where you take a picture and you compare the brightness of your target star to the brightness of other stars in the frame. I guess that's actually pretty hard with really, really bright stars because there aren't too many stars like Betelgeuse in the frame of Betelgeuse.
True. That is another issue with doing super bright stars. There are certain ways to get around it, and what you can do, not many people actually take this tack, but you can observe the bright star and then switch fields to another bright star and then go back. So you're kind of doing this nodding effect in essence so that you can get a comp that is relatively similar to the star that you're looking at. A lot of people will also observe with much wider fields when you're observing these super bright stars because you kind of have to. But if you're trying to do like very precise measurements of super bright stars, some people will use what are called photometers or SSPs. They don't make those anymore, but they are ideal for that very specific measurement because you look at one star and then you look off at a different star and you're just basically going back and forth. You're not getting a full field. You're just looking at one star at a time. And so you can kind of replicate that effect with CCDs by this nodding thing, but you are correct, not easy, especially as you go super bright. Yes?
If you have a very bright star like Betelgeuse, and in the field surrounding it there are enough fainter stars, you could make a comparison if you have valid exposure. Could you take very short exposures of Betelgeuse and longer exposures for the field stars and make your photometric comparison between them, taking into account the difference in exposure between the field stars and the
I would be hesitant to do that. I think you could, but you'll run into issues where your exposure time is different, your dark current is different, your systematics are slightly different. So when you're trying to compare things, there's a lot of different small things that might have, that can feed into errors in that method. I don't think it's impossible, but it's not something that I've heard someone ever try. I guess you could try it and see how well it worked, but yeah.
I'm kind of facing this problem. I've been monitoring people aboard since May every year, not getting the 75 images. And this is fine now because it's 10th magnitude or so, and in the field, there are a dozen or so stars that I can make a very nice log plot of magnitude versus signal, and people aboard, on the low end of that, I can easily get a magnitude. But the only red star in there is Stellafane borealis, and it's only 4th magnitude. So when the thing pops its cork, I'm not going to have much to compare it with, other than these Stellafane borealis and all these fainter stars.
Yes, that is definitely a problem. We did try to go as bright as possible, but at a certain point, there just aren't any stars that are reasonable. I think that the best option would probably be to try to do this sort of go off field. That might be better just because you can keep the exposure time the same and your systematics as close as possible. But I will definitely ask around and see if we can't give some kind of more dedicated lecture to how this would work. Because I think it's a valid point and a point that people probably, but not just you, but multiple people are struggling with. And I think that's something we could probably give a more dedicated webinar or something on to sort of give people ideas and places that they can, to make that easier.
What I've been thinking of doing is Caltech is pretty close by. It's outside of my field of view, but I could go back and forth, and it's second magnitude.
Yeah, I think that's a pretty good idea. I thought I saw a hand over here earlier, but I do not now. Okay, if there's nothing else, I'll be around all weekend. Please come by if you have any questions or you just want to talk to me. I'm more than happy to do that. And thank you for listening.